Hi there, this is John Plesiga again, here to give you a quick high-level overview of the DWSim simulation software we use for our initial testing of working fluids. So what you see on the screen here is our very basic Rankine cycle setup. We have the fluid input here, and just really quick, the way DWSim simulation works is you have these material streams right here, where this is going to be our working fluids, and then you have these energy streams. And at different points where there's components, it calculates what the energy stream needs to be and what changes in the material stream. So starting with one, and what we did here is this is where we can change the compound amounts. Here we're just all isobutane. And then we have our initial conditions found here. And we're using temperature and pressure. And what happens is it runs through this cycle. It's a closed loop. This is where it recycles. I believe it's 10 to the 6 iterations for this example. It runs through the pump, and this pump, the components are on this data sheet here, and requires about 53 watts of power. This is how the isobutane changes after the pump. It then goes into a very basic boiler. There's no real heat exchange here. It's just kind of constant heat input. So after that, we have the material stream data here. The heat added is right here, about 23 kilowatt. Then it goes to the turbine, expands and condenses slightly. And it goes through our condenser here. Just some things of note with this example is everything has a limited efficiency. So the pump efficiency is right here, 85. Both the heat transfer units are at 87, and the turbine is at 75.1. These are pretty low estimates, but also accurate for what you can find for residential grade components. And the biggest issue with DWSim, well, one of two. The first was it ran great with this example, and then we tested it with water using textbook example from thermal power plants. And the textbook example, the pump work and the expected gas water, vapor water mixture was the same as the textbook answer, but the work out of the turbine was off by nearly 20% error, which isn't great. So what we used the simulation for in the end was just kind of a rough estimate, just to get the ball rolling. The other thing that became a problem with the simulation is that you see right here, we're using CoolProp as the property package, and that's just kind of the calculations that goes on. A lot of this simulation is run under Python script, and you can see here that is using CoolProp, and that's using CoolProp. But this model has other equations it could use. It could use the Ping-Robinson and the SRK equation modules, and those calculations are a little bit different. Their inputs and outputs are a little bit different, and it tweaks the simulation sometimes a little bit, sometimes quite a lot. And fine-tuning the simulation, because the user interface is so easy, it isn't quite simple to understand and to tweak to figure out the errors with the textbook and to give us a better model. So like I said, we use this as a base, as an example, and then we ended up developing a MATLAB function that gave us a better error rate with textbook solutions. And it also used the CoolProp property. And just while I have it really quick, when I say CoolProp, it's an open source database that's a lot like RefProp, and RefProp is just a national database for different thermodynamic properties of all kinds of working fluids. And that one you have to pay for. CoolProp is open source. It matches the RefProp data very, very nicely. And so it uses those pretty much those steam tables. So we use Cooper up here, it works great. And then with the MATLAB function, which I'll introduce in a little bit, we also use the CoolPro package. That's all for this simulation. If you have any questions, please feel free to reach out. My contact information is available. Thank you.